All right, today we're going to dive into a powerful and honestly kind of paradoxical idea in software design, building systems that are literally designed to fail. And I'm not talking about some abstract theory here. This is the bedrock of systems that handle billions of users. Think WhatsApp, and those ultra-reliable telecom switches that have powered our phone networks for decades.
This sentence right here, it says it all. Instead of trying to bubble wrap your code and prevent every single possible error, this approach just accepts that, hey, things are going to go wrong. And it builds a super resilient system around that very fact. It's a total shift in how you think about building software.
And that's the million-dollar question, isn't it? It just sounds completely wrong. But the answer lies in this really brilliant and elegant architecture that turns what would be a catastrophe into just a routine, totally manageable event. So let's break down how that actually works.
So, this whole let it crash model is built on one single fundamental concept: isolated processes. Everything starts right here.
The absolute key phrase you need to hear is shares no memory. Just imagine each process is living in its own completely sealed room. Nothing one process does, no matter how badly it messes up, can directly mess with the memory or the state of any other process.
And here's the kicker. These processes are incredibly cheap. I mean, so cheap that you can spin up millions of them on a single machine and it won't even break a sweat. They're designed to be disposable, created and destroyed by the thousands. And that cheapness is absolutely essential for a strategy that involves, letting them crash and just starting new ones.
So this is the crucial takeaway, that isolation creates containment. A failure in one process is kind of like a fire in a sealed, fireproof room. It just burns itself out right where it started, without any chance of spreading to the rest of the building. This is the first huge step to building a reliable system out of parts that you know are going to be unreliable.
Okay, so if a process fails inside its own little isolated room, how does anyone else know it even happened? How does the system know it needs to fix something? Well, that brings us to the next piece of this puzzle: signaling.
Right. This is the challenge that isolation creates. If they can't peek into each other's memory, they need some kind of formal way to communicate their status, especially the status of, hey, I just crashed. And Erlang gives us two main tools for exactly this. Let's look at how these compare. A link is like a super intense, codependent relationship. If one process in a link dies, it sends an exit signal that by default takes the other one down with it. Think of it like a three-legged race. A monitor, on the other hand, is more like a passive observer. It gets a little note, a down message, when the process it's watching goes down, but its own life isn't on the line. Getting this distinction right is absolutely vital for building the right kind of structure.
So we've got our isolated processes, and we've got ways for them to signal failure. Now, let's put it all together. Let's see how Erlang's OTP framework, that's the Open Telecom Platform, organizes all of this into a resilient, self-healing architecture called the supervision tree.
The whole system is basically divided into two simple roles. You've got workers, which do the actual work, handling requests, running calculations, all the application stuff. Then you have supervisors. They don't do any of that. Their one and only job is to be the manager, watching over their workers and making sure they get their job done. And these roles aren't just tossed in a pile. They're organized into a really clear hierarchy, a tree structure. You have supervisors watching workers, and you can even have higher-level supervisors watching other supervisors. This creates a really clean, totally predictable chain of command for handling any failure anywhere in the system.
Okay, check it out. Here's a healthy supervision tree in its natural habitat. Up top, Supervisor A is the big boss, overseeing everything. It manages Worker 1 and Worker 2 directly, but it also supervises another supervisor, Supervisor B. Supervisor B is then in charge of its own team, Workers 3 and 4. Right now, everything's humming along just perfectly.
But we all know things don't always run smoothly, right? So let's introduce a little bit of chaos. Let's say Worker 3 hits a bug, some completely unexpected error, and boom, it crashes.
And there it is. Worker 3 has crashed. It's gone. Now, in a lot of systems, this is a 5-alarm fire. It could corrupt data, block other requests, or even set off a chain reaction that brings the whole thing down. But in this design, it's just business as usual.
Because Supervisor B was linked to Worker 3, it gets an immediate exit signal. It doesn't have to poll or check or guess. It knows instantly that its child process is gone. The failure has been detected, just like that.
And here it is. This is the magic of the whole philosophy in action. Supervisor B's only job is to handle this exact situation.
So it immediately starts a brand new, squeaky clean instance of worker 3, putting the system right back into its known healthy state. And this all happens in microseconds. The rest of the application never even had a clue there was a problem.
So what's the end result of all this? What's the big payoff? Well, it completely reframes our relationship with failure. Failure stops being a disaster you have to fear, and it just becomes another event that the system is built to handle.
The whole principle really just boils down to these 3 simple steps. You structure your code into these distinct roles, you organize them into a hierarchy, and then you just trust the system. You get to focus your energy on the happy path and let the supervision tree handle all the inevitable exceptions.
And let's be clear, this isn't about ignoring errors. It's about containing them and recovering automatically. The system becomes self-healing because that recovery is baked right into its core structure, not just bolted on as some kind of afterthought.
This quote from the official docs points out a really important side benefit. This isn't some chaotic, anything-goes approach. It's a formal, structured pattern, what OTP calls a behavior, and it makes the code predictable and way easier to maintain. You always know exactly how the system's going to behave when something goes wrong.
And that's the thought I really want to leave you with. This whole philosophy, it goes way beyond just one programming language. It's a mindset. What could you build if you weren't terrified of failure, but instead you actually planned for it from day one?